let us get back to the discussion we were having yesterday. If you may recollect, we were talking about pulse shaping from the point of view of eliminating intersymbol interference, and we have introduced now a set of pulse shapes or family of pulse shapes which are appropriate for this purpose, which satisfy the so-called Nyquist's first criterion. Right? This family of pulse shapes, if you may recollect, is basically an extension of the idea behind the sync pulse itself, but unlike the sync pulse, these family of pulse shapes occupy more spectrum than they occupy more bandwidth than the corresponding sync pulse. Right? The sync pulse has this brick wall kind of spectrum, whereas these pulses have a more gradual roll off, decaying smoothly to 0 rather than suddenly to 0. And the net result of that is that you get the desired feature of zero crossings at regularly spaced intervals of t0 seconds at the data rate, but instead of having very large side lobe levels, you have very small side lobe levels, and also the asymptotic rate of decay is also quite high. It's 1 by t cube as against 1 by t square, 1 by t of the sync pulse. So therefore we call these practical pulse shapes for eliminating intersymbol interference. This is the so-called race cosine family. It is practical from 2 points of view. First, it is perturbation tolerant to timing errors. Right? Any perturbations that may take place in timing will be tolerated much better, causing much less intersymbol interference in the case of these family of pulse shapes than the sync pulse itself. Similarly, it is also practically realizable more easily because the kind of spectrum that they have is easier to approximate with real life circuits than this kind of spectrum. Right? You can appreciate the difficulty in realizing a spectrum of this kind, which has a sudden fall, a very sharp transition, whereas a spectrum which has a fairly gradual roll off is much easier to realize by real life components like RLC components. Suppose you were to decide to do it by using only a passive filter, you could do so by approximating this gradual roll off characteristic with an appropriate rational function, because RLC circuits can only realize rational functions of frequency, ratio of polynomials in omega, right? So you can approximate this by a suitable polynomial and then realize that rational function by means of an RLC circuit. There are approaches to do that, or you could do it by some other means, but the fact that it is gradual roll off enables a practical approximation, renders the practical approximation to be much easier than the one which has this kind of characteristic. Okay? Of course, we are not going into that aspect at all at the moment because of time limitations. Now, so far so good. The question that might arise from here is the following. What we are seeing is that the minimum bandwidth required to transmit at f0 is f0 by 2, right? The Nyquist frequency or the Nyquist bandwidth. And if you want good perturbation tolerance, what we have argued so far is that we need excess bandwidth over and above the minimum. A question that people asked was, is it possible to get rid of the menace of intersymbol interference, also have the nice desirable feature of perturbation tolerance to timing errors, and still use not more than the minimum bandwidth? That is a question that is of interest today. Okay? And the answer to that is yes or no? Should be yes, because I am asking a question, right? But it is yes with a qualification, and the qualification is you don't completely eliminate intersymbol interference. You in fact introduce a certain amount of intersymbol interference deliberately at the transmitter itself. The only difference is, since it is being introduced deliberately and by design by you, you know precisely the manner in which this intersymbol interference is taking place and can eliminate it in an appropriate manner at the receiver, can take care of it in an appropriate manner at the receiver. Rather than this intersymbol interference taking place on the channel in an unknown manner, you are allowing it to take place in a designed manner so that you can later take care of it, and the moment you allow this kind of a thing, it is possible to do what we just wanted to do, namely get all the three features in one. Three features being perturbation tolerance, using minimum bandwidth, and good realizability, easy realizability, right? So let us see how we can do that. And this in fact brings us to Nyquist's second criterion for which deals with this issue. The Nyquist's first criterion was based on eliminating intersymbol interference altogether, whereas Nyquist's second criterion, instead of saying we should eliminate it altogether, permits a controlled amount of intersymbol interference to take place in the pulse design itself. Okay, that is the essential difference. Now, what it helps to do therefore is the net effect will be we will be able to double the transmission rate, right, as compared to, let us say, the raised cosine family with r equal to 1, raised cosine pulse with r equal to 1. There the bandwidth required was f sub 0, here it will be f sub 0 by 2. So if you are transmitting at f sub 0, using this kind of a technique, you could double your transmission rate and still have good tolerance to timing errors, right? So either you could double the transmission rate or half the bandwidth and still have good tolerance. Right?
Doubling is compared to raised cosine.
Doubling is with respect to raised cosine with r equal to 1. With respect to r equal to 1 case. Of course, if you are using the sync pulse, then we are not gaining anything. But then the sync pulse doesn't have this tolerance. So we want both the features together. We want bandwidth efficiency as well as good tolerance. These are the two features which we want together to be present. Whereas as far as the raised cosine pulse is concerned with r equal to 1, we have achieved good tolerance to timing at the cost of bandwidth efficiency, right? That is something that you must appreciate. Now this is, it looks very interesting and surprising, but actually it is a fact which was known even to early telegraphers when the only kind of communication that used to take place was by dots and dashes, by manual Morse code kind of transmissions. Even they knew about this, that if you have a communication system which supports transmission of, let's say, dots, because dots are the ones which occur faster, at a certain rate f0 or f0 by 2 whatever, one could double the rate to from f0 by 2 to f0 on the same system by just a simple trick of reinterpreting the received data. This was a trick known to them as long as about 80 years ago or more, even before Nyquist formulated this in a proper analytical fashion. Now I'll illustrate this fact by an example. So I'm not at the moment coming straight to the Nyquist criterion, but just trying to motivate it by means of an example. Let's say we are back to our polar signaling, right, with rectangular pulses, with full width rectangular pulses being used, right? So let's return to our polar signaling. Let's say over a system of rate communication system which can support transmission of f0 bits per second, or f0 digits per second, or f0 symbols per second, right? And let's say the pulse shape that we are going to use, PT, is the rectangular pulse, full width rectangular pulse. Okay. So suppose we have this arrangement, our good old polar signaling. This is the bandwidth available to us. This is the data rate that we can use, and the pulse shape is full width rectangular pulse. So what we are perhaps transmitting is either this pulse or this pulse. Alright. Now since it is band limited to f0 and f0 is reciprocal of t0, right, the received pulse will not look like this, isn't it? You are passing this pulse through a low pass filter with bandwidth approximately the reciprocal of this duration, right? Can you make a guess what kind of received pulse you are going to get? You will get a smoothened out pulse. It will rise slowly to some peak value and then decay slowly to some peak, to some whatever is the value here, right? This is where you are going to. So it's, let's say, going to rise to some value plus k volts. When you transmit a 1 using PT of this kind, at the what you are going to sample at t0 is this peak value k, on the basis of which you might try to decide whether a 1 or a 0 was transmitted. Similarly, if you had transmitted a 0 by a negative pulse minus PT, this will slowly build up to a value minus k, assuming a symmetry of operation and everything going ideally. Okay, so under ideal conditions, at the sampling instant t0, you will see an amplitude either plus k or minus k. Okay, on the basis of which you could decide whether a 0 or a 1 is being transmitted. Now suppose I double the transmission rate, which essentially means that I am now going to, let me use a different color for that. I am now going to use pulses of half the width, right? Instead of using a full width pulse corresponding to t0, I will use a full width pulse corresponding to t0 by 2, right? But the response to this pulse is going to be same. So instead of building up to the full amplitude, I will build up to this value, right? Similarly, here instead of building up to minus k, I will build up to this value. That is, I will not be at the end of t0 by 2, I will not be able to see the complete response or the complete build up of the pulse which is expected out of that channel if you were to transmit at a slower rate, right? Is that clear? Therefore, doubling the bandwidth obviously is going to create trouble in this channel because my response is much smaller as compared to what I could have expected at the end of the full pulse interval. Right. However, now suppose I were in this double rate situation were to transmit a sequence of 2 ones. What will I get? I will get a full width pulse again. If I transmit 2 successive ones, effectively I am transmitting a full width pulse, and if I sample it here, I will get a plus k value. Similarly, if I get a sequence of 2 zeros, I will be transmitting 2 pulses of this kind, and I will again build up to minus k value. So this will build up to plus k at t0, this will build up to minus k at t0, right? And if it was a sequence of this kind, either a 0 followed by a 1 or a 1 followed by a 0, what will happen? at this point the response will become 0, right? So now all I do is I operate at double the speed, but I make an interpretation not by just observing plus k and minus k, but I observe whether it is plus k, minus k or 0. If it is plus k, I know that the present bit is 1 and the preceding bit was also 1. If it is minus k, the present bit is 0 and the preceding bit is also 0. And if it is 0, the present bit is the opposite of the previous bit, right? So if I make an interpretation table of this kind, then I'm in business. I hope you appreciate that. So I think let me make this table here. Our interpretation table now will be something like this.
To distinguish between 0 and 1.
Let me just finish this, then we'll come back to your question. So received amplitude is k. Interpretation is that the transmitted digit in the present interval is 1 and the previous value also was is also 1. If it is minus k, it is 0 and the previous value is also 0. If it is 0, it is the complement of the previous bit. So somehow if I knew my starting bit, then I am in business, right? Suppose the starting bit was always fixed to be 1, I am in business. Is it clear?
So you take 3 bits, you're considering 3 bits. 2 ones in the
I'll basically what I'll do is I'll sample at every t0 seconds and make a decision. Okay? Corresponding to the previous bit.
So why don't we do sampling at twice the speed?
You'll be sampling at twice the speed. I'll be sampling at t0 by 2, t0, 3 t0 by 2.
No,
Of course, for the first bit, very first bit, I'll sample at t0. After that, every t0 by 2 seconds. Right?
So we will be sampling at every t0 seconds.
No, because I need to make a continuous decision regarding the present bit as well as the previous bit.
So could
Right?
So if we sample at t0, then we'll.
I think that is trivial. You can just check up yourself. This hardly requires any explanation.
Just we'll draw that-
Because you need to look at each pair of successive pulses, and pulses are being transmitted at a rate of reciprocal of t0 by 2 now. Right? So every pair of successive pulses with overlapping of one pulse, right? So that you can, in fact, it will also give you an error detection capability to some extent, right? Because if you find an inconsistent decision over 2 successive decisions, then you know that there is some problem.
So
Yes.
is it a half bit pulse or a full bit pulse? The discussion right now.
It's a full width pulse since your interval signaling interval is no longer t0, it is t0 by 2. But with respect to the old signaling interval, it is half width. There is a confusion.
So if there are 3 ones continuously and
There can be any number of ones continuously, right? It doesn't matter. Only thing is, suppose I have it. All right. Let me take a fresh page. Let me try to resolve your doubt. Suppose you have a sequence like that, right? Let's say initial bit is always known to be 1. So I look at this point. If the we expect the received amplitude to be here plus k.
So could you draw that again waveform here?
Right.
Like you draw the waveform transmitted.
Waveform will behave like that. Let's assume that it's building up and building down in the same way that we just described.
The problem is about the half wave and full wave part. The half wave looks
See, all that will happen is because we're transmitting at double the rate, instead of building up like this, it's going to go like this. And there's going to, if the next one, the next pulse transmission is like that, it will start building up like this. This is the one. So the waveform is this kind, right? Either it's building up or it stops here and starts building down. These are the only 2 options at any stage, right? It builds to here or it builds further or instead of going in this direction, it comes like that. If it is coming like that, either it can go like that, or it can go like that. So those things will not change, right? So whatever I have discussed for one pair will continue to hold for every successive pair. So here it will build up to k, it will build up to 0, to 0, to k.
How will it build up to 0?
So the point is that suppose it builds up to k and then there's a 0.
Yes, sir.
It won't go down to 0. It won't go down to 0. Yeah.
Something like
So it will be k by 2.
0.69.
So that's why he was saying that T
That's why we are saying that first we should sample at T0 by 2 and later on after every T0.
After every 0.
The first
Yes.
sampling should be at T0.
Okay, I think you are right.
Sir, that's the confusion.
Yeah. Okay, that's right. The sampling rate is at
You're always
t0
assuming the previous bit to be
because
0.
we are sampling every t0 seconds, and at t0 seconds we expect the waveform to be building up to either plus k or minus k or 0. Okay.
So, could you just take a sequence of 1 0 1 0 and show how it behaves?
All right. Let's see. 1 0.
1 0.
All right. So
we always assume the first bit is starting bit is 1.
we have to make some
So we
assumption.
put
Let's
a 1 in the
so let's look at the waveform.
It's better, sir.
इससे तो कुछ नहीं पता चलेगा.
ये तो सारी है.
This is what you are transmitting.
This is a full bit first.
This is what we are normally transmitting. Now if you transmit at double the rate, okay.
Yeah, even if I sample at T0, even then it doesn't solve that problem.
That's all.
Okay.
You remember the time.
extra 1 डाल रहा था तो उसे
Let's talk only of these 4 bits at the moment. So in this case, it would have built up like that, right? Now it will build up like that, and then it will build down like that, right? Build up like that, and so on.
So that's the point. Like,
Now, therefore, if I am sampling here, right, I knew that this was 1. I am sampling here, so since this is 0, I know that this bit must be opposite of this. So this becomes,
so but this is not according to the logic that is given here.
this is according to the same logic.
हाँ ठीक तो है.
ठीक है, this is okay.
The first bit I know is 1, right? Now I am sampling here at t0 and finding that the value is 0, and that tells me that the polarity of this bit should be opposite of the previous bit.
Fine.
After this point, it's
So
fine.
this is 0.
Now, yes or no?
So again,
We'll get 0.
When you sample T0 by 2.
No, you have to sample at T0 by 2. Yeah, you have to sample at T0 by 2.
okay, there is a problem here.
यहाँ पे 0 आया तो
So the sampling doesn't make any difference. The point is this logic is wrong.
What happens here? That is a question.
These are 3 T0 by 2. So we're something like double.
So I guess all it means is there are situations where this logic will fail, right?
Sir, if we are closer,
So,
it should not be there. So
Why?
we are doing something.
So interpretation table, we should have more entries corresponding to K by 2.
I wanted to deliberately keep it to
So I think there should be 3.
only 3 level system so as to motivate the duo binary system, right?
Then
If you permit more levels, yes, what you are saying is possible, but I think at the moment, perhaps I should say that this is something which may work most of the time, but may fail occasionally, right? After all, this is just an ad hoc way of doing things, right? It was just motivating you to what I really wanted to
keep
get you.
track of the previous we have detected a 0 and out there we have again got a 0. I mean at
There has to be
the
1, sir.
the point at which you
Yeah, one way of doing that would be that I was
if
thinking
you
about
keep
that.
track of the previous 2 or 3 bits, then you can do it, sir.
It looks like it, but we have to make sure that all possible combinations will be taken care of like that. Yes, he's quite right. See, suppose if I sample it here and I find it 0 here again,
0 again here, so it will be
but this could correspond to
minus 1 0 1 0.
0 1 or 1 0,
1 0.
right? But if you keep track a bit way down in the past,
Then it is 1.
then this won't be
So
possible.
actually, sir, what we can do is we can have
Why? Because if we had a 0 followed by a 0, I would have built down to minus k, which it did not do.
Yes, it is 0 1.
No,
Sir,
you
we
would have
have.
built down to minus k.
Sir, in our-
You were starting from plus k by 2, so you would have gone down to minus k by 2.
Sir, in our interpretation
You
table.
would have brought it up back.
so in the interpretation table.
Oh,
we
you were
just-
gone down to minus k by 2.
Yeah.
Right.
So we need to have levels, 4
Yes,
levels,
you're right.
and
It would have gone like that.
No,
Okay, I admit there is some problem here. It's not fully explainable.
Sir, it's all
I
right,
think
sir.
I don't. Is it all right?
So because we should get a 1 there, because we are saying in the interpretation table that if it is 0, then it is complement of the previous bit. Previous bit is 0, so it has to be 1. So again 1 0
Keep track
1.
of the previous 2 or 3 bits, then we'll definitely do it.
Yes, sir. So because previous bit is 0, so this bit should be 1.
I think we'll leave this for a moment. I'm not totally convinced about your argument.
Sir, what is the interpretation table? We have said that
If we
If
are
one
getting
of you speak at a time, perhaps we can discuss.
if we are getting a 0 at one point,
Yes.
and we know that two bits before that we got a 0, then the 0 has to be followed by a 1, sir.
yes, sir.
And then it has again come back to 0.
or when 0 0 1.
For example, here there is no way to know whether this is a 0 or a 1 here, because I could have got this point either through this path or through this path. There is no way for me to find out. Okay.
So, but if you sample at t by 2, then
If I sample at t by 2, either have to permit another level,
Yeah.
which I don't want to do for my motivation, or I have to do something
You
else.
have to introduce.
So there is some problem here, which we'll take cognizance of, and I think leave it over here. The primary purpose of telling you this example was that a thing like this was possible under certain conditions, may not be under all conditions. Okay, so I think we leave it at that with some limitations. It is not the main point of our discussion anyway. So, but unfortunately, my motivation has not succeeded fully. But it happens. All right. Maybe I'm making some mistake, but at the moment I can't think of where the mistake is.
maybe we can transfer a 1 after every 2.
We'll leave it for the moment. We'll not work with any more wild suggestions. All right. Anyway, basically, what I wanted to motivate was, which I slightly failed in doing so properly, that really speaking, the basis of this trick that at every 2 successive ones will make it build up to plus k, and every 2 successive zeros will make it build to minus k, and a 1 0 0 1 combination will make it build to 0. That is similar to the logic of the Nyquist's second criterion. Let us hope we will not find a similar problem with the Nyquist second criterion. Maybe after understanding this, we can come back to this and see if we can resolve this issue. Now, this criterion is for the design of a pulse shape, right? What it says is that let us choose a pulse shape PT such that, see, earlier what we said was PT is equal to let's say some constant at t equal to 0 and 0 at every other sampling instant plus minus nt0, right? Here we are permitting some non-zero values other than just the central value. In fact, we are not even going to look at the central value, right? We are looking at these values, the values of the pulse at plus t0 by 2 and minus t0 by 2. Our receiving strategy will be based on looking at not the peak amplitudes at the signaling points, but t0 by 2 away from the signaling points. T0 by 2 seconds away from the signaling points. At these two signaling values, it says let us have some constant c as before, but there are two of them now instead of one, right? At plus t0 by 2 as well as at minus t0 by 2. But it is 0, so this it is c at these 2 points, it's 0 for, I shouldn't put this here, p plus minus n t0 by 2, for n, let me separate this out, n equal to 3, 5, 7, etc. So if I draw this time axis t, at minus t0 by 2 have some non-zero value, at plus t0 by 2 have some non-zero value, but from there onwards at intervals of t0 seconds separated from t0 by 2, t sub 0 by 2, at all these points the values are 0. So we are looking at some pulse which passes through these points, right, which has 0 here, this amplitude here, 0 here, 0 here, 0 here. For example, I could have some pulse shape like that. Okay, that's what the Nyquist second criterion is all about. Designing a pulse shape such that we may have intersymbol interference from two successive pulses, but not from far removed pulses. Okay, basically that's the idea. So such a pulse, is it okay? We'll discuss it in more detail now. I've just introduced the basic definition to you of the second criterion.
What about the even part? You were saying about the even.
E1, what is E1?
Like even multiples of T naught. Multiples of T naught.
Are you talking E1 and odd?
So he's saying multiples of even
But we have
multiples
said
of
n 0357. What
Yes.
about 246?
Oh, that's because I want zero crossings only at these points. You see, the first non-zero value I'm looking at is at t0 by 2. From there onwards, every t0 seconds, I want a zero crossing. Because what I'm going to sample is at not these points. My sampling points are not going to be these. My sampling points are going to be these.
Right. So you will have ISI coming from the previous sample.
Right. This is precisely what I was going to explain next. Okay. These are going to be my sampling points. Sampling points are going to be not at multiples of t0, but at multiples of t0 by 2, and obviously since my sampling interval has to be t0, I have taken odd values here. There is no need for even values. Okay, I am not going to look at here or here. Alright. Can I remove this slide now? So what will happen is that such a pulse shape will cause or will be associated with zero ISI if I sample at points which lie midway between signaling instants. Okay, that is plus minus 3t0 by 2, plus minus 5t0 by 2, and so on. So if I sample at these points, I am assured of zero SI, right, from other pulses, except with one exception. What is the exception? Except the points which lie midway between the current around the neighboring midway between itself and its neighboring transmissions, except the points lying midway between itself, that is the current signaling interval, and its immediate neighbors. Okay, that is t equal to plus minus t0 by 2. Now, if you understood this broad idea behind this pulse, let us get to the question of how do you synthesize or how do you specify a pulse of this kind with minimum possible bandwidth. We should not lose sight of our bandwidth requirement, right? We want to continue to use the minimum possible bandwidth. So the next question that arises is, we will look at the functioning of this a bit later as to how we will decode our data using this pulse. Let us forget that for a minute. Let us just look at the question of what kind of pulse shape should this actually be so as to give this kind of characteristic, this kind of behavior at the sampling instance, and also have the minimum possible bandwidth, namely the Nyquist bandwidth. Can you think of a construction procedure? It is logically very simple, in fact. Question is not clear. Synthesize a pulse shape having these kind of values at the sampling instance as prescribed here, and having the minimum possible bandwidth associated with it corresponding to the signaling interval T0.
Combination of sync pulses.
That's right, a combination of sync pulses. Each sync pulse will be having that minimum Nyquist bandwidth, right? So if I take two sync pulses which are mutually displaced from 0 by minus t0 by 2 and plus t0 by 2 and linearly combine them, I will have all the desirable properties, right? Should be obvious, because shifting them to either minus t0 by 2 or to plus t0 by 2 will shift their peak values as well as the zero crossings. But both these sets will have zero crossings at odd multiples of t0 by 2, right? So when linearly combined, the zero crossing points will stay the same, but the nature of the central lobe will change, right? And that's the kind of pulse shape we are likely to then get. So if the motivation behind it is clear, the maths is then very simple. What we have just argued is that if we restrict this Pt to a bandwidth of f0 by 2, f sub 0 by 2, then the only pulse shape that you can think of is, in fact, this is just some amplitude factor, not very important. The sync pulse displaced by t sub 0 by 2 and the sync pulse f sub 0 t minus t sub 0 by 2, right? Fine. Are you all with me on this? Which again, if you simplify, it's very straightforward simplification, will turn out to be equal to this function. That's a mathematical function of the pulse shape corresponding to this construction procedure. If you are not followed, please let me know so that I can repeat it. Anybody who wants to repeat this, or is it okay? Good. The power spectrum of this is also very easy to evaluate, because we know what is the Fourier transform of each of these. It is a rectangular function with the bandwidth f0 by 2. So basically these are two rectangular functions associated with a phase function e to the power minus something, right? When you combine those two terms, it will become cosine function. We will get e to the power minus j omega t0 by 2 from here, e to the power j omega t0 by 2 from here. Both of them otherwise are rectangular functions which will factor out. So it's quite clear without going through the formalities that the power spectrum would be a cosine function multiplying that rectangular function. Right? Cosine function coming from these two shifts, time shifts. In frequency domain they will become exponential functions, and e to the power plus j omega t0 by 2 plus e to the power minus j omega t0 by 2 will essentially give rise to this. The rest are normalization factors which you can take care of. Okay. What does it look like? It looks like this. That's your power spectrum. You see, it's confined to what this says here is there should be, it's a rectangular, the overall confinement is between omega 0 by 2 to plus omega 0 by 3. That's the significance of this product function. This function, rectangular function, which is multiplying this cosine function, right? And within this, that constant value is being multiplied by this cosine function, right? So you once again you have a cosine kind of function here, and this pulse shape given by this expression looks like this. Okay. You have at minus t0 by 2 you have some constant value, at plus t0 by 2 you have some constant value, but at all other multiples, odd multiples of t0 by 2, that is here, 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 you have 0 amplitudes as desired. Any questions regarding the construction and the spectrum of this pulse? Since there is no question, I believe it should be all right. Okay. Now let's try to understand, if we use such a pulse shape, how do we really go about interpreting the received data and decoding the correct sequence. So one thing is clear, use of this pulse shape will allow us to work with full bandwidth efficiency, right? Because we are not going beyond the Nyquist bandwidth. Also, intuitively you may expect this to be a well behaved pulse shape otherwise in terms of its side lobe levels and things like that, right? Because we don't have a sharp transition in the spectrum. We have a gradual roll off, right? There is no sharp transition. So it will be very easy to approximate. Also, the corresponding pulse will decay rather quickly. In fact, the mathematical function here shows the rate of decay asymptotically. It's 1 by t square, right? It's not as good as the raised cosine pulse with r equal to 1, for which it is 1 by t cube, but it's still pretty good. It's 1 by t square, all right, asymptotically. So it has those perturbation tolerant features. It uses the minimum Nyquist bandwidth, right? These requirements are met. The only thing left to do is to understand how exactly we will decode the data when we use such a pulse. Okay? Let's get to that. To do that, we'll have to think of the we'll have to talk about the coding scheme, which will be same as the polar scheme as before. That is, we'll say 1 will be represented by Pt of this shape, 0 by minus Pt, right? And at the receiver, what we'll really be doing is sampling at multiples of t0 by 2, odd multiples of t0 by 2, right? So what we know then is this is going to be equal to some f sub 0 by 2 and is going to be 0 for n equal to 3, 5, 7, etc. I think best thing is to can you now well, in this case it turns out to be f0 by 2, isn't it? For the specific function that we have finally constructed, pt equal to this, its amplitude is 2f0 by pi, which is the peak value, which we are not looking at. We are looking at these values, right? Okay. Now, similar to the argument that I gave for the telegraph situation, which we were not fully comfortable with, but something similar to that holds here also. When we transmit two digits of opposite polarity, what will happen? At the midpoint, I think I best illustrate by a diagram. I don't know whether you'll be able to draw this in the time that we have here, but I think it's more important to understand than to draw this picture, right? Let's say I have a 1 followed by a 0, right? For this 1, I have this blue waveform that is transmitted, right? This is the peak of the waveform. Kt0 is the signaling interval, right? That is corresponding to the symbol interval, a symbol time kt0. This is where the peak value builds up, but at the receiver, of course, I am not looking at this value. I am going to look at t0 by 2 seconds later, right? The next one is a 0, which is a negative pulse of this kind. The only difference between these two is one is positive, the other is negative, and there is a mutual displacement of t0 seconds, right? If you look at the resultant waveform of these two transmissions, that this black curve is what you will get, right? You will find you are going through a 0 crossing at kt0 by 2, kt0 plus t0 by 2, right? So a 1 followed by a 0 will result in a 0 amplitude at the next sampling instant.
So 1 followed by 0 will result in a 0
amplitude
in between the two something.
at the next sampling instant.
This is 0 followed by 1.
This is my next
You're
sampling
sampling in
instant.
between the two.
That's right.
So
My sampling instant is not here now, as I mentioned earlier. It is going to be here.
So midway between the two.
Midway between the two. No, midway between two signaling instants. I'm now differentiating between signaling instants and sampling instants, right? Corresponding to the signaling instant kt0, I'm saying the sampling instant is kt0 plus t0 by 2.
So what do you actually mean by a signaling instant?
That is, the pulse actually arrives here at time kt0, but I'm not looking at the pulse, the peak value at this point, but I'm looking at t0 by 2 seconds later.
So not able to understand what do you mean pulse actually arriving here at t0.
Well, it's in a loose sense that the peak of the pulse lies at kt0 in this context. Okay, it's in a loose sense. The pulse has arrived, of course, long time ago, right? Because of the tail. There is a long tail with the pulse. Similarly, you can argue, I think it's quite obvious, a 0 followed by a 1 would be again resulting in of course it will be building up like that, and 0. A 1 followed by a 1 would lead to a situation of this kind, the blue curve followed by the red curve, and the resultant curve would be this, right? Now if you look at the midway point here, no, it will build up to some peak value. Okay, yes, it will build up to f0 because both of these are f0
by 2.
right?
Both are
this,
f0.
this is also f0 by 2, this is also f0 by 2, and the result will be
f0.
f sub 0.
So how are they f0 by 2? I don't know what you understand.
Okay, I didn't go through the maths of that. I think that will come if you evaluate that function at t0 by 2. You will find that that function reduces to f0 by 2. Okay, I skipped a bit of algebra. Okay, so let's see what will happen. What I have plotted here is what will happen when I transmit a sequence of ones and zeros with an arbitrary set of pattern. Right? You have 1, 1, 0, 0, 1, 0. Now if you were to put all those pulse shapes over here and find the resultant waveform, this is what you will see. Okay. So sampling it here will give rise to 1. Sampling it here will tell me that will tell me that there is a change in polarity.
So here also you assume that the first one is a 1. First bit is a 1.
No, here it doesn't make it.
Why?
It doesn't make it.
Yes. We have to assume that the first bit is a 1. Quite true. Because without that we don't have a reference to start with.
Peak won't come.
So that is required. So here again we have since it is 0 followed by a 0, this is again a change of polarity, again a change of polarity, and so on. Right? Of course I have stopped here because there is no I have not specified the next bit. So the kind of situation we get is something like this. Let's say this is a transmitted sequence. Let's construct the waveform first. As to, if you look at the samples of the transmitted waveform xt, what will that look like at the signaling points? This one is, let's say, the initial one which you fix. Since the next value is also 1, we expect the waveform to build up to f sub 0, right? Since the next one is 0, it will return to 0. Next is 1, again it will return to 0, and so on, right? And then it will be reinterpreted correctly. So basically the logic is similar to what we have discussed earlier, that if you receive f sub 0, interpret that the current digit is 1. Minus f sub 0, current digit is 0. And if you get a 0 amplitude, there is a change in polarity. A transition is to be interpreted. So which is similar to what we tried to motivate in the beginning, but I hope in this case there is no problem. It doesn't look like.
Current digit is the one.
Would you again take a 1010 in this case?
So before that is current digit.
I will have to draw that waveform very carefully because there is a sync pulse involved, right? I may not be able to do it very easily over here, but we can try out that exercise. We can try out that exercise. Yes, what is your question?
The current digit refers to T02 after the sampling is started.
That's
after,
right.
because the first one,
Transmitting.
not the preceding one, succeeding one. Because preceding one we know right from the start. So when we receive the first F0, we know there's a 1 in the first one, so the one after it will be 1.
That's
So we
right.
start detection of the succeeding one.
That's right.
That is what you mean by current digit.
Quite true. Any other question? So this is what is called, in fact, before I tell you what it is called, do you see something interesting in this transmitted pattern of samples?
If they are separated by odd number of zeros, then same.
Something that you have seen before
Dual binary.
in dual binary signaling, right?
Transparent.
What you find is
Odd number.
that
Even number of zeros. Same,
Even number of zeros.
Same polarity.
separate amplitudes of same polarity, and odd number of zeros separate, let's say between these two, between amplitudes of opposing polarity, right? Which is precisely what you learned in your dual binary signaling. But then that was obtained from a line coding point of view. This is obtained from a pulse shaping point of view, right? This is the result of the way we have carried out our pulse shaping, right? And we are looking at the receipt pulses, right? So therefore, the Nyquist second criterion pulses are essentially dual binary pulses, dual binary signaling schemes of some kind. Another thing another name that is sometimes used for this kind of signaling is called partial response signaling, right? Partial response signaling. I'll mention it here.
So, but this happens at the receiver. And what
Yes,
you're transmitting is unique.
that's right. This is what you are looking at the final.
What are the advantages of dual binary?
What are the advantages of what?
Dual binary.
This is
The
what is
advantage is this, that we got everything that we wanted. We have used only the Nyquist bandwidth. We have got 100% bandwidth efficiency. 100% is a wrong way to use it here, but in some sense it is 100% because this is the minimum required and we are using only that much, right? We have perturbation tolerance.
But you have the problems of on-off signaling.
Like what? Which problem? Not that of on-off signaling. This is polar signaling.
Sorry, polar signaling. Yeah, right.
Those disadvantages may be there, right?
what disadvantages may be there?
Whatever disadvantages polar signaling has, those might continue, right? Because we are considering polar
But is it
signaling.
bipolar?
Polar is bipolar.
Dual binary is bipolar.
It's not bipolar, it is really dual binary. Yes, it is bipolar in the sense that it has got 3 levels, right? But yes, it is bipolar signaling. So it is okay. It's not even polar. Thanks for pointing that out. It's not strictly polar. Although our scheme of allotment of 1 and 0 is polar, that is, we are allotting a PT to 1 and minus PT to 0, the net result is that the sample values exhibit a bipolar kind of dual binary kind of behavior. Okay, so we have everything that we want in this kind of scheme. In fact, everything except one thing. Can you tell what is the factor which is still missing?
Sir, if one bit is in error, then there will be detransmission.
Okay, that's a minor problem. We'll come back to that. The important point that we have discussed before is that the DC is not 0, right? So that is something we'll try to remember. How much time we have? Oh, we have crossed the time. I'll just take a couple of minutes to tell you the point that has just been mentioned, that in this kind of decoding scheme there is a problem, particularly due to this third entry here in this table, right? We are talking of a transition. Transition means it assumes that you know your previous digit correctly, right? Suppose there is a mistake in that due to noise or whatever, then the error will propagate, right? Now this kind of thing can be easily taken care of by pre-coding the information at the transmitter itself, by carrying out some kind of coding of your binary data at the transmitter itself. Perhaps we can take care of in the next class.